Hi, how you doing? My name is Bob Lee. I'm an applications engineer and trainer with RF Venue, and there we go. And that's me in the photo. I kind of look like this too. Um, I've been with RF Venue since the beginning of the year. I've worked in live sound, mostly in theater sound. Uh, you know, doing working with wireless mics, and I've been an RF geek most of my life, playing around with antennas and stuff like that. I'm a ham radio operator. I worked at QSC for 27 years also, so I've been in pro audio and live sound and stuff like that for many years. So, if you're not familiar with RF Venue, we make essentials for wireless audio to make wireless mics and inner monitors work better with better performance and reliability. So that's our specialty. So this is just a quick look at our range of products. We have antennas here at the top, RF systems in the middle, and our spectrum tools. Now, one thing that might jump out at you is that our antennas don't look like anybody else's antennas, and nobody else's antennas look like ours. And that there's a reason for that. We take a really a different approach to uh, designing and making antennas, and you know, try to address some of the issues that maybe other manufacturers have not taken up. So, by the myth of active antennas, what do we mean? It's I would say it's the myth that if you're putting together a wireless system, you need to buy active antennas. You see that often. It's like if you're gonna, go to a dealer and buy a wireless mic system, you want so many channels, you want so many mics and receivers and stuff. Oh, got to get active antennas, and that's not the case. We're going to look at why most applications, vast majority, do not require active antennas, and in fact, it's more flexible if you go with passive
Okay.
antennas.
Yeah.
So here is a look at an actual active antenna scenario. We have the antenna circuitry right on the antenna. And then somewhere down the line, we have to have some DC injection, putting in the operating voltage for the antenna circuitry. Now, fortunately, putting DC and UHF radio signals on the same coax cable is not difficult. It's really easy to keep them separate, even though they're flowing on the same cable. So in the antenna circuitry, we have an inductor to decouple the DC voltage from the RF, and we use a capacitor to keep the RF energy from going into the DC, and they can coexist pretty well. Now, if you have bandpass filtering, that would have to be further downstream because bandpass filters typically don't pass DC. So this is you know a typical active antenna scenario. Now the antenna is right up front. It's going to bear the full brunt of the RF signals, and you can't install a bandpass filter before the circuitry. This might cause more problems than it solves. Okay, so let's look at what we're trying to achieve with our um, with our wireless mic system. We want to get signal in the receiver that's at least about 20 dB above the noise floor. Okay, so it's a pretty simple goal, and we have to look at how we accomplish that. In this diagram, we have four wireless mic signals. Two of them are really in good shape, more than 20 dB above the noise floor. This third one over from the left, that's got something going on the same frequency. That could be an issue. And this fourth one that is stuck, right into a digital TV signal, which is not a good situation. But if we can get this 20 dB above the noise floor, we're in good shape because then the receiver will achieve what's called capture effect. And so because we're using FM signals, they're frequency modulated, so the signal is not holding onto a signal frequency, it's jumping around with the audio modulating the carrier signal. The receiver does not have a fixed frequency to lock onto. It has to lock onto the signal that's jumping around in frequency. But with capture effect, the receiver is able to lock onto it and not get pulled away, lock onto a competing signal or some noise or something like that. So we'll get good reception that way. So, key strategies to optimizing the performance and minimizing dropouts. Well, first of all, you should scan your RF environment to know what it is, and also coordinate frequencies, hopefully based on that scan, also, so that you can avoid potential interference. Use appropriate antennas with good polarization performance. Now, this gets into why RF venue antennas are not like other companies' antennas. This is the polarization performance. So we'll take a look at that. Now, between the antenna and the receiver, you should try to keep the active circuitry as minimal as possible. Now, you can't get away from it when you're doing a distro because you're splitting up the signal. You have to have some gain to make up for the reduction in the signal levels when you split it up. So that's the essential active circuitry that you need to have, but you should really try not to have any other active circuitry. And we'll get into why we do that. Now, any active circuitry that you do have in the signal receiving path should have high dynamic range. That is low noise and really high headroom, so that it can handle a wide range of signal levels without going nonlinear. Now, the thing with small signal RF amplifier circuitry, they tend to be reasonably linear with small signal levels, but they get more nonlinear with larger signals. And that just has to do with how you have to design RF circuitry. It's a little bit more complicated than designing, say, audio circuitry. Audio circuitry is pretty easy to make a circuit linear, a little bit tougher with RF circuitry. It's kind of like if you look at the Earth around you, it might look flat. But if you take a really, really wide view of the Earth, you can see that it's curved. Same thing with the transfer curve of a typical transistor amplifier used in RF. Put the bandpass filter before any active circuitry. Anytime we can keep out unwanted stuff from getting into your active circuitry, that's a good deal. So in most cases, that would be, on what's going into the distro. And with an active antenna, we can't do that. We can't filter the active circuitry at the antenna. Okay. So also use high quality cable, coaxial cabling, appropriate length, not too long. You don't want to have a whole bunch of excess length of cable. And also be careful of the bend radius when you're going around a corner or something like that. Make sure that you do not make a really tight bend because that will deform the cable. Now, attenuation in RG8X cable over the 400 to 700 megahertz range, which includes the UHF spectrum that we use with wireless mics. It ranges from 7.9 to 11 dB per 100 feet. So, we have to understand that we're losing signal in any significant length of coaxial cable. So let's look at what happens in linear circuitry or passive circuitry. When you have multiple signals in passive or linear circuitry, those signals coexist perfectly well together. And the receivers have no problem at all picking up their signals, their respective signals, and everything's fine. You'll see this in the actual antenna part of the circuit of the system, in the coaxial cable. or if you have active circuitry, if it's really super linear, this will be the case. Now, what happens if we if the signal, if the circuitry is nonlinear, like if we overdrive the circuitry, then we get some nonlinearity. We start crunching the signals. The waveform is not the purely complex waveform that we have when all these 9 signals are coexisting perfectly. They start intermodulating with each other. They're not coexisting anymore. They're producing um, some and difference frequencies. This is called intermodulation distortion. And these frequencies start, they fall within the band of frequencies that we're trying to use for our wireless mics. So they raise the noise floor. And this this comes into play because some of these signals might fall on or near the carrier frequencies of the wireless mics we're trying to receive. And if that happens, we can get a dropout. Either the audio goes away, or we get a noise hit, like an RF hit, or perhaps even distortion. You get uh, when you get when you have intermodulation, it's because of multiple signals, intermodulating with each other, and they're producing intermodulation signals, and so they're going to be this very ugly combination of several audio signals together, modulating that intermodulation um, product. And that could, if the receiver latches onto that signal, it's going to sound really bad. So we want to keep the linearity of the receiving system from the antenna into the receiver as linear and pristine as possible. So that means we really have to be careful about adding unnecessary active circuitry into the equation. Now, if you have uh, active circuitry that's designed with a high dynamic range in mind, then you have more headroom, and so this intermodulation will be less likely to occur. Now, we can look at using antenna directionality to our advantage. The CP beam by RF Venue has about 10 dB front to back gain, so we can make up for reduced signal just by having an antenna that has more gain to the front. And now the thing to understand about antenna gain is that it's passive. This is a good kind of gain. It's not from active circuitry. This is done from just having designing the antenna so that uh, its reception reinforces in the good direction and tends to cancel out in the directions that we don't want to receive in. So if we have a directional antenna, we can have a pointed toward the transmitter and get a better pickup of the transmitted signal, and we can ignore to some extent any interfering signals from other directions. So the CP beam has a pretty good front to back ratio. The diversity fin, that is 2 antennas in one. If you're not familiar with it, that is a diversity pair in one unit. So that has a front to back ratio also of about 10 dB on the vertical part. It also has a horizontal dipole that is a little bit more figure 8 shape, but it also has a little bit more sensitive to the front. So we can use antenna directionality to our advantage. Use the passive gain of the design of the antenna to give ourselves a really good signal level that will hopefully get us beyond that 20 dB threshold that we want. So another thing to understand about antennas is how they react to a polarization of the transmitted signal. So this is a really cool video that one of our people found that demonstrates how the polarization of the antenna and polarization of the transmitted signal really affect each other. So here's a couple lengths of wire which form an antenna, because all antennas are essentially wire, even if they're like a copper or aluminum rod or traces on a circuit board or something like that. They're essentially wire. Okay, so there's a little light bulb in the middle. So this in front here is a handheld transceiver, and we're going to look at how this works with different angles of transmitted signal. Look at that. There's enough RF energy coupled into that wire to make that light bulb light, but at a crosswise angle, that reception falls off. So this is why RF venue antennas don't look like anybody else's antennas. We addressed this issue. This same phenomenon is why, even with diversity, straight paddles and a diversity configuration, we still sometimes get dropouts on both antennas at the same time. Now, if you get a dropout on an antenna, if you could somehow freeze time, if you're a master of time and space, and you take the antenna that has a dropout, and if you could turn the angle on it, rotate it, you would find that, oh, the signal comes back as long as there's a direct line of sight between the antenna and the transmitter. Well, what if you have an antenna that doesn't happen to? So that's even better than having some boost in signal at the antenna, is just to have the antenna be sensitive to any polarization of the received signal. And that's why we offer antennas that are impervious to the polarization of the received signal. So we have the diversity fin, which is two antennas in one unit. There's a log periodic directional antenna, essentially a paddle, like other paddles, but it also has a horizontal dipole attached to, it's essentially co-located to the paddle portion. So we have a diversity pair in one unit. So as long as this antenna is pointed toward the transmitter and it has a clear line of sight to the transmitter, it's not going to drop out. It's going to get a usable signal no matter what. And that's important because with wireless mics, we can't control how the singer holds the mic, what angle the singer holds the mic. We can't control how the actor wears the body pack, or how he or she angles his or her body. This is a moving target, this polarization of the direct signal. So we need to have an antenna that can pick up any of those polarizations. So we also have the diversity omni antenna, which is an omnidirectional in the horizontal plane. It has a vertical element plus a horizontal folded loop. So it doesn't matter what direction the signal is polarized in. It's going to pick up on one element or the other, and that's all you need for diversity reception. You don't need to have good signal on both antennas, although it's nice when that happens. You just need at least one antenna to be there when the other one doesn't pick it up. So that's how the diversity omni works. That also is a diversity pair in one unit. Now, because it's omnidirectional, the applications where you would use that are kind of limited. It's not quite as useful as having a directional like the diversity FIM, but there might be some um, situations where you need an omnidirectional antenna. Now, the omnidirectional antenna is going to pick up in all directions, so um, it's less likely to reject interference from unwanted directions. So the other alternative is to use two CP beam antennas. Now, the CP beam antenna is really cool. It's a directional helical antenna, so it's circular polarized. So circular polarized antenna that can pick up a polarized signal of any direction. It's now limited to just vertical, and horizontal, any angle in between, it's going to pick up. So for diversity, you would use two of these antennas, and you have a really super, I would call it the Superman of diversity antenna systems. So these are alternatives to putting an amplifier on the antenna. Just do something better with the reception um, characteristics of the antenna, and you don't need that amplification. Okay. So getting into coaxial cables. Now, coaxial cables have can have okay, an appreciable amount of loss in our UHF range. So I got this chart from windsystem.org. If you look at like 400 megahertz and 700 megahertz, that contains the UHF spectrum that we're using, which is 470 to 608 megahertz. So at 400 megahertz, RG8X has about roughly 8 dB of loss per 100 feet. So if we have a 54 antenna cable run, 400 megahertz, okay, it's going to be half of that, so 4 dB, but we're using something higher than 400. So let's say 500 megahertz, it's going to be more like around 5 dB, 4.5 to 5 dB of loss in 50 feet. 700 megahertz, that has 11 dB per 100 feet. So again, a 50-foot run, it's going to be half of that, 5.5 dB. These are not insurmountable amounts of loss. Because remember, the background noise picked up from the antenna is also going to be attenuated. So we can still have that 20 dB signal to noise, even if we lose some of that signal coming down the coming down the cable. So if you really need to cut down on losses, like let's say you have a very long run, say 200 feet or more, there are other options. You can go to other lower loss coaxial cables, and we also have fiber optic solution for really long runs. And LMR 400, that's another popular cable, but because it has lower loss, it's more expensive, bigger and thicker, and not as easy to work, but it's available if you need a lower loss cable. But in most cases, regular RG8X works extremely well. So let's look at the optimal solution for antennas that don't need these are solutions that don't require an active antenna, but can work perfectly well for your situation. Use passive antennas with better reception characteristics. Use antenna gain and polarization patterns to your advantage. So this is what we discussed earlier. Use distro with high dynamic range. That would be a low noise figure and high headroom. So we have products that do that, like the Distro 5 HDR, which is new, the older Distro 9 HDR. So if you really manage things well with your distro system, you can, accommodate a wide range of signal levels without getting, any appreciable intermodulation. For very long coaxial cable runs, like let's say 200 feet or longer, you might not want to use RG8X, but maybe use an optical fiber system like our Optics 3, or at least a very low loss cable. Um, Use inline amplification as really a last resort. Now, by absolutely necessary or last resort, I mean, let's say you have a really weak signal from a transmitter that you can't make up in passive gain of the antennas, um, and you can't make it up any other way. And also, your background RF noise level has to be very low. Because when you amplify that weak signal from the transmitter with an active antenna or an inline amplifier, you're going to be amplifying also the background noise that the antenna picks up. So keep yourself flexible. Don't handcuff yourself. Use a passive antenna and have inline amplification as like a last resort option. You can always add that in. You can take it out if you don't need it. But I always advise don't start with an active antenna. It's it it might just prove very limiting to you. Okay, and then install bandpass filters at the distro inputs, or if you do use inline amplifiers, put them on the inputs to the inline amplifiers. Okay, so we're nearing the conclusion now. I want to add that if any of you are going to the AES convention in New York, I will be leading a panel discussion called Best Practices in Wireless Audio for Live Production. And that's part of the technical program of the convention. That's going to be Tuesday, October 8th at 9 a.m. in room 1E07. Okay, there's more information at aesshow.com. So, any questions? Fire away.
Awesome, Bob. That was a great presentation. Certainly, if you guys have any questions from Bob's training, you can put them in the Q&A and we'll try to field them. But you submitted a lot of questions. We can't get to all of them, but we picked a bunch that we're going to call out. So let's see. Let's start here. The first one is there a good practical use for active antennas as they'll bring up noise floor too?
It's that's the problem with active antennas. Sometimes you might need them, in a situation like I mentioned where you have a really weak signal from the transmitter, but you also have a very low uh, noise floor, background noise floor. In a typical urban environment, you might have a lot of RF noise, and just putting an amplifier on an antenna is not going to solve your problem, because you're boosting that weak signal from the transmitter along with all that background noise, and you might not get that 20 dB relationship between the signal and the background noise.
Awesome. Next one. If I have to use an active antenna, should I start at the lowest possible gain selection, 0 dB or minus 6 dB?
Uh, I would start, try what you can. If you're really wedded to the situation of using an active antenna, try to use as little gain as possible, and just just try to get by with uh, with a lower setting, and you can, I would, try it empirically, you see if the signal level is adequate for your receivers. If you have to bump up, then bump up only as much as needed.
Cool.
Okay,
So a good live question just came in from Gustavo. Why should I connect the bandpass filter before the inline amp?
that's that's to keep out um, unwanted signals. You see, with that slide that showed what happened when you overdrive a signal, or when you overdrive a active circuitry, and you get all this intermodulation. Now, you can get that overdriven condition with signals that you don't know about, like TV channels and mobile phones and stuff like that, that's out of band. But when they intermodulate with the signals that we want to use, they produce interference that's right in our UHF band. So by keeping unwanted signals out of the circuitry to begin with, we end up with a much cleaner situation in the active circuitry. I hope
Excellent.
that answers the question.
Absolutely. The next one's a good one. So give us some real world stage scenarios when to use forward gain versus omni.
Well, generally in most situations, you want to use a directional antenna that has forward gain, that has is more sensitive to the front because you can point it at where the action is going on, and you'll be less sensitive to um, interfering signals coming in from other directions. Now, the omnidirectional antenna is really for if you're going to have uh, people with wireless mics kind of like all over the place. And they're not going to be in one particular area. You can set up an omni kind of in the center of action and pick up in all directions. But most situations in live production, there's theater, music, whatever, even film production, film and TV production, the action is going to be taking place in a certain direction from where the antenna is. So if you point the antenna, a directional antenna, at the action, that's usually the best way to go.
Great. Yeah. So positioning the omni is very critical. You want that in the center of your coverage area.
Yeah.
Okay, this is a really good one. Why use passive antenna with good expensive cables when I can use an active one with cheap cables, getting about the same signal to noise ratio?
Oh, the problem with using cheap cables is that you're not going to get the same signal to noise ratio. The cheap cables typically don't have good shielding. Now, the thing with coaxial cables is you're dealing with RF signals, which are both an electrical wave and a magnetic wave. That's what radio signals are. Now, the shield around uh, a center conductor, that only actually acts as a shield to electrical fields. It contains the electrical field of the signals inside the cable between the center conductor and the shield. Now, what it does for magnetic waves is that if you, um, well, magnetic interference only will get onto the coaxial cable if there's a difference in the magnetic wave between one conductor and the other. But by putting one conductor inside the other, they're essentially occupying the same points in space. So there's not going to be any induction of magnetic interference in. So coaxial cable with good shielding kills interference both electrically and magnetically. If you have cheap coax cable that might have gaps in the shielding, well, let's call them holes in the shielding. That relationship between the center conductor and the outer conductor is not going to be maintained well through the length of the cable. And so you're not going to get a good signal to noise ratio if if your coaxial cables are cheap and poorly made.
Great. Got a couple more questions here. So this one should be pretty easy. RF signal to wireless receiver. What's the difference between the DFIN versus an active paddle, for example?
Well, an active paddle will, depending on how much gain you have, um, well, that'll affect, how much signal you're putting down the line. Now, you might be putting more signal than, the distro wants to see. You might actually be overdriving the circuitry in the antenna. There are a lot of uh, there are a lot of variables with the active situation. Now, the the paddle part of the D-fin is really works very similar to a passive paddle from any other brand. All these paddle antennas work largely the same way. They're a log periodic directional array, just a bunch of antenna elements essentially printed onto a printed circuit board. That's really what paddle antennas are made from, is a circuit board with copper, uh, and they're relatively inexpensive to manufacture that way. And so the D-fin, the vertical paddle, is going to act really largely like a regular passive paddle, but you also have the horizontal dipole, so that at that point in space, it's going to pick up a signal of any polarization.
Great. This is a really good question considering the topic. Can you address the use case for the RF spotlight?
Well, our spotlight is it seems kind of counterintuitive because it's a reduced sensitivity antenna. Okay, so it's circular polarized. It's like a big black pancake, essentially, about a quarter of an inch or so thick in the middle. Um, and that has reduced sensitivity, but it's made for being put on a stage or a dais or podium or whatever, um, or maybe an altar. It's for close pickup. That reduced sensitivity works in our favor because the wireless mic transmitter is only a few feet away from the antenna instead of 50 or 100 feet or whatever. So you would use at least two of them for diversity. Um, I met a guy who does RF coordination for the NHL for their outdoor games, the Winter Classic games, and that's a big festive occasion because they set up a stage and have recording artists play like before the game and during the intermissions. He was telling me about a setup he did for Brian Adams at one of these. So he set up a bunch of spotlight antennas, A, B, B, A, B, B, so that he created all these diversity zones up on the stage, and he picked up the wireless mics perfectly well, and yet it was more impervious to all the 5G phones in the audience, the 40,000, 50,000 people in the stadium. It was impervious to the RF from all the media organizations there. And it was a perfect solution in that case. That's a kind of odd situation where the RF spotlight comes into play. It's a circularly polarized antenna. I think I might have mentioned that, but so it picks up the wireless mic at any angle, and like I said, it's reduced sensitivity, so it picks up the close-up signal really well and can ignore the further away stuff that you don't want.
Great. We've got one more live question here. Oh, and as there's more questions coming in as I say that, but looks like we only have a little bit more time here. Thanks for all your awesome questions, by the way. Bob, could you speak to the advantages or disadvantages of a DFIN antenna versus the spaced pair of LPDA antennas? Well, multipath diversity versus polar diversity.
Okay. The problem with single polarization antennas is you can get dropouts, like I we demonstrated in that video, just from the transmitted signal hitting the antenna at the wrong angle. Single polarization antennas are great for about 300 degrees of the possible angles that the signal can hit the antenna at. It's when it approaches like 70 to 90 degrees off the plane of the antenna, that's where we really lose the signal, we lose the reception. And there's nothing in having another antenna that's the same thing and oriented the same way. That same phenomenon can happen on the other antenna at the same time as well. There's nothing to prevent that from happening. Just setting up two antennas for diversity really just increases the mathematical reliability of the situation, but it doesn't take care of the phenomenon of polarization changes. So the D-fin, in a looking at a certain point in space, if that point has a direct line of sight to the antenna, to the transmitter, it's going to pick up a signal one way or another in some angle that either the vertical or the horizontal element can pick up. And so it's not going to drop out. Okay.
Great. I think that's all the time we have today. It was a really great question, guys. Definitely let us know how we did. I'm going to send you a feedback form. So definitely give us some
Hey,
information and any topics you'd like to see us cover. We're always happy to help. And you can reach the team at any time at info@rfvenue.com. We all look at that email. So if you have more questions that weren't answered or you'd like to us to explore another topic in depth, just let us know. We're happy to do so.
Adam,
So
real quick
yes,
here. I
yes.
just want to add to the presentation. I'm Richard. Hi, nice to meet you. Definitely adding to this, and if you consider what tools we would use to see this, is put a spectrum analyzer like our RF Explorer before it hits the receiver, and you could see the noise. You could see the reaction of an antenna based on your
Yeah.
walking. So putting in a spectrum analyzer and walking your transmitters are really going to help show all this information to you.
Mm-hmm.
So
Yeah.
Great. Yeah, and we're happy to help you with any troubleshooting and walk testing procedures because the guys
Yeah.
do that every day here. So we're always happy to help with any questions, whether it's a
Or
sales
even
question
if you,
or tech
yeah,
question or whatever.
even if you just want to bounce ideas off of us,
Yeah, if you've got
we're
a
here to help you.
complicated idea test, RF stuff is definitely mysterious. So we want to help
Yeah.
demystify it at
Yeah.
every step of the way. So thanks everyone for joining. Thank you, Bob. Thank you, Richard. Thank you, Don. I saw you were answering some questions in there, Don. Appreciate your support. And again, just let us know if we can help in any way with any of your RF projects. And we're looking forward to seeing you ask us more questions. So thanks again. Take care, everybody.
Okay. Thank
I
you.